Around 12,900 years ago, the last ice age was ending. Things were warming up and glaciers were starting to recede. And then something happened. For about 1,200 years, the climate reversed and got colder again. When this cooling trend ended, the ice age was finally over, and it also happened to coincide with the rise of agriculture and human civilization. Learn more about the Younger Dryas, some of its possible causes, and how it impacted humanity on this episode of Everything Everywhere Daily. This episode is sponsored by Mint Mobile. If you're a regular listener, you know that I spent over a decade traveling all over the world. During my travels, I would often get mobile plans for my phone, and I noticed that almost everywhere in the world had much, much cheaper phone plans than what we had in the United States. That all changed with Mint Mobile. With Mint, you can get monthly plans that start at just $15 a month. That's why I recommend Mint Mobile. All plans come with high-speed data and unlimited talk and text delivered on the nation's largest 5G network. Use your own phone with any Mint Mobile plan and bring your own phone number along with your existing contacts. At Mint Mobile, their favorite word is no. No contracts, no monthly bills, no overages, no hidden fees, and no BS. Ready to say yes to saying no? Make the switch at mintmobile.com/EED. That's mintmobile.com/EED. Upfront payment of $45 required, equivalent to $15 a month. Limited time new customer offer for first 3 months only. Speeds may slow above 35 gigabits on unlimited plan. Tax and fees extra. See Mint Mobile for details. This episode is sponsored by the Turkish Airlines Series podcast. I want to tell you about a podcast that I think some of you might enjoy, the Turkish Airlines Series. The podcast fuses storytelling, culture, and practical insights to bring destinations to life. Each episode transports listeners and viewers into real places like Istanbul, Cappadocia, and Mediterranean hideaways via personal stories from creators and travelers. Of course, Turkish Airlines is the perfect company to have such a show, as they fly to more countries than any other airline in the world. Having been to over 200 countries and territories around the world myself, I've flown Turkish Airlines many times, and I've also had the opportunity to spend time in Istanbul, which is one of my favorite cities on earth. So if you're into travel, culture, or just want a fresh listen, subscribe now to the Turkish Airlines Series. You can find it on Spotify or Apple Podcasts. Just search for Turkish Airlines Series. The Younger Dryas might not be something that you've heard of. It's mostly been a concern for Ice Age researchers. However, it has become more relevant recently for reasons I'll get to shortly. So let's start with the simple question, what was the Younger Dryas? The Younger Dryas was a sudden and severe cold period that interrupted the general warming trend at the end of the last ice age. It lasted from approximately 12,900 to 11,700 years ago, representing one of the most dramatic and rapid climate shifts in Earth's recent geologic history. The Younger Dryas is named after a small Arctic alpine flower called Dryas octopetala, which became abundant in pollen records during the cold interval. Dryas grows today in tundra and subarctic regions, so its presence in ancient European sediments signals a return to cold glacial-like conditions. European scientists studying lake and peat deposits from the late Pleistocene found several distinct layers rich in Dryas pollen, each representing a cold phase. They labeled them the Older Dryas, the Middle Dryas, and the Younger Dryas in chronological order. The Younger Dryas was the last and most recent of these cold episodes, occurring just before the onset of the stable Holocene climate, which is the geologic epoch that we're currently living in. Next question. How do we know that the Younger Dryas took place? After all, we didn't have thermometers back then. Evidence for the Younger Dryas comes from multiple paleoclimate proxies that all register a sharp millennium-scale return to cold conditions beginning about 12,900 years ago and ending abruptly about 11,700 years ago. The clearest evidence is found in Greenland ice cores. Stable isotopes of oxygen and hydrogen show a sharp drop in inferred temperatures over years to decades, alongside increases in wind-blown dust, sea salt, and calcium, indicating stronger, colder, stormier conditions over the North Atlantic. These ice cores also trap ancient air. Methane concentrations fall at the onset of the Younger Dryas, consistent with a contraction of northern wetlands, and then rebound rapidly at its end, a pattern that matches the temperature shifts. Lake and marine sediments independently mirror this same story. Lakes in Scandinavia, Germany, and Japan preserve year-by-year changes in sediment composition that mark colder, drier, and more erosive climates. In Venezuela and North Atlantic cores, finely layered sediments and microfossils show sea surface cooling and changes in plankton communities. Glaciers add a physical record. In Scotland, the Loch Lomond moraines captured a pronounced glacial re-advance that aligns with the Younger Dryas. Glaciers in the European Alps, the Andes, and New Zealand also advanced or stabilized, marking cooler conditions. And finally, cave deposits, which can be dated precisely by uranium-thorium methods, provide some of the best geologic clocks. Stalactites and stalagmites from caves in Israel, China, and elsewhere display abrupt shifts in oxygen isotopes that track regional climate responses to North Atlantic cooling. These records all indicate that the Younger Dryas began relatively quickly within decades and ended just as rapidly about 1,200 years later. If you remember way back, I previously did an episode on Milankovitch cycles. These are long-term cycles based on the tilt of the Earth's axis and the precession of its orbit around the Sun. These cycles can affect the amount of sunlight hitting the Earth, especially in the northern hemisphere, and can change the planet's climate. So if you're wondering, this couldn't be responsible for the Younger Dryas because these cycles work on the scales of tens to hundreds of thousands of years. The next big question then is, why is this important? If the Earth happened to cool down for 1,200 years, over 11,000 years ago, why is that relevant? If you have been paying attention, that date, about 11,000 years ago, has cropped up again and again in various episodes. This was the earliest time that we can point to the domestication of crops and animals, as well as the earliest human-made structures such as Göbekli Tepe in Turkey. When the Younger Dryas ended about 11,700 years ago, the climate in the northern hemisphere shifted from a volatile, near-glacial climate to the relatively warm and stable conditions of the early Holocene epoch. That change happened fast on human timescales, with decades to centuries of abrupt warming. The new baseline reduced the frequency of extreme cold spells and reorganized winds and rainfall, which, in turn, expanded grasslands, forests, and wetlands. For people who had endured a millennium of cooler, drier conditions, this meant a broader and more reliable number of plants and animals, longer growing seasons, and predictable water on the landscape. Once the climate settled down, experiments in saving seeds and corralling animals could pay off across generations, rather than being undone by a change in the climate. With the sudden climate rebound, fields of wild wheat and barley expanded again, and the incentives flipped towards permanent settlement and active cultivation. Over the following centuries, those experiments hardened into the domestication of cereals and pulses, followed by sheep, goats, and later cattle. Similar events unfolded independently in other regions as climate stabilized regional water cycles. In the Yellow River Basin, in the Yangtze wetlands, along the tropical regions that supported maize and squash in the Americas, and in the high valleys that nurtured tubers in the Andes, the new climate created ecological windows where repeated planting, harvesting, and selection could finally produce results. None of this means that the Younger Dryas by itself caused civilization. Social innovation, local ecosystems, and cultural choices were essential, and civilizational timelines differed in different regions. The end of the Younger Dryas, however, created a stable environment and a burst of ecological productivity, making cultural evolution more likely to persist over generations. If the improved climate served as the carrot, then the extinction of large megafauna may have also served as the stick. As temperatures rose and ice sheets retreated, tundra and steppe habitats that supported mammoths, woolly rhinos, and giant bison were replaced by forests and wetlands. The specialized grazers that thrived in open, cold environments suddenly lost their food sources and range, while smaller, more adaptable species survived. The decrease in large animals, which were the focus of most nomadic hunting societies, may have necessitated many of them to become more settled, a change that was now possible in a warmer environment. So the Younger Dryas was very important in the development of human civilization, and there's plenty of evidence that we can point to for its existence. However, there's one thing I haven't touched on yet, which is a topic of great debate and controversy. Why did the Younger Dryas happen? What was the reason why the Earth's climate so quickly reversed for over 1,000 years and then reversed again almost as quickly? The leading theory is called the meltwater pulse hypothesis. As the ice sheets over northern Europe and North America melted at the end of the last ice age, large proglacial lakes formed on their margins. A proglacial lake is just a body of water that forms in front of a glacier or ice sheet, created when meltwater becomes trapped by the ice itself or by moraines and other debris left behind as the glaciers retreated. This theory suggests that a freshwater influx from the glacial lakes disrupted the Atlantic Meridional Overturning Circulation, or AMOC, which is the ocean conveyor belt that brings warm water northward. Freshwater is less dense than saltwater, so the influx may have prevented the normal sinking of dense salty water in the North Atlantic that drives this circulation. Without this heat distribution system, the northern hemisphere cooled dramatically. There are different theories on the routing of this meltwater. Some evidence suggests that it flowed through the St. Lawrence River into the North Atlantic, while other data points to routing through the Mackenzie River into the Arctic Ocean or the Mississippi River into the Gulf of Mexico. All of these are physically plausible and consistent with the pattern of the strongest cooling occurring around the North Atlantic, with smaller changes in the tropics and southern hemisphere. A second, less popular theory, at least among professional geologists, is known as the cosmic impact hypothesis. Proposed in 2007, this controversial theory suggests that a comet or asteroid impact or airburst over North America triggered the Younger Dryas. Proponents argue that a disintegrating comet or meteor airburst ignited widespread biomass burning, darkened ice, and perturbed atmospheric chemistry, which then caused rapid cooling and perhaps helped destabilize ice margins to release meltwater. They cite layers with elevated nanodiamonds, magnetic sphericals, shocked minerals, and sometimes a carbon-rich black mat at sites in North America and elsewhere. Critics counter that these signals are kind of patchy and that some claimed impact markers are produced by ordinary terrestrial processes, and that there's no confirmed crater of the right age and scale. The proponents then reply by noting that if it was an airburst, like in the Tunguska event, which I covered in a previous episode, there wouldn't be a crater. And there also wouldn't be a crater if it hit the ice sheet itself, which also would have caused a catastrophic release of fresh water into the ocean. While meltwater pulse and cosmic impact are the two most widely debated theories, they're not the only ones that have been proposed. Volcanic forcing has also been proposed, particularly in the large Locher Sea eruption in the Eifel region of western Germany, which occurred very close in time to the Younger Dryas. Any major volcanic eruption will inject sulfate aerosols into the stratosphere, reflecting sunlight and cooling the surface for a few years. This happened after the Mount Pinatubo eruption in the Philippines in 1991. Advocates suggest that such a short-lived cooling, superimposed on a climate system already primed by meltwater, could have nudged the Atlantic circulation into a weaker mode that persisted for 1,000 years. The main objections are that volcanic aerosol effects are too brief to explain a 1,200-year event on their own. Additionally, precise dating places the eruption slightly before the full onset of the Younger Dryas, which weakens a direct causal link. A fourth line of thinking treats the Younger Dryas as an internally generated oscillation of the ocean ice atmosphere system that was tempered by slow orbital changes, but not directly caused by them. In this view, the North Atlantic has multiple stable circulation states. As ice sheets retreated and freshwater flows varied, the system crossed a threshold that flipped it into a cold, sea ice-rich mode without requiring a single external shock. Once in that mode, strong sea ice and environmental feedbacks reinforced the cold, and only later did the background warming and changes in freshwater balance allow a rapid return to the warmer conditions. There's no single smoking gun that commands universal agreement on the cause of the Younger Dryas. The agreement of many records on an abrupt surge of fresh water in the North Atlantic and a weakened ocean circulation system makes meltwater forcing the most widely accepted driver of the Younger Dryas, with the debate focused on exactly the routing of the fresh water and whether the freshwater release was catastrophic or more gradual. But regardless of how it happened, the Younger Dryas, or more specifically, the end of the Younger Dryas, is one of the most important events in the history of humanity. This abrupt warming and the end of the Ice Age ushered in a host of changes, which included agriculture, animal domestication, and monument building. All of which were the first steps in the very long journey in the creation of human civilization. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oetken and Cameron Kieffer. My big thanks go to everyone who supports the show over on Patreon. Your support helps make this podcast possible. And I also want to remind everyone about the community groups on Facebook and Discord. That's where everything happens that's outside the podcast, and links to those are available in the show notes. As always, if you leave a review on any major podcast app or in the above community groups, you too can have it read on the show.